Right, we are looking today, first things first, at what we call the electromagnetic radiation. Electromagnetic radiation is extremely important for us to discuss because it is part of the curriculum. So there are certain things we need to first focus on, and we look at the fact that there is actually a relationship. First, we know that the frequency, right, the frequency and wavelength and wavelength relationship. Relationship in electromagnetic waves. Okay. In electromagnetic waves. Right, so we know that this relationship can be seen as the following, where C equals F lambda, like so. Right, where C is what? What does C stand for in this formula, Leander? What is C? Have you seen this formula before?
Yes.
Okay, so what does C stand for in this formula?
Um,
It stands for the speed of light in a vacuum. And what is this speed of light in a vacuum? What is it? It is 3 times 10 to the power 8 meters per second. That is what the C stands for here. What does F stand for in this formula, Luyanda?
frequency.
Well done, frequency. What does lambda stand for in this formula?
The wavelength.
Lambda represents the wavelength. Lambda represents the wavelength. Okay, I want us to look at an example. First, let us look at an example that is going to assist us to master these with ease. The frequency of the radiation in a microwave, in a microwave oven is 2.45 gigahertz. You need to proceed to calculate its wavelength. We look at the solution to this one. Okay, the frequency of the radiation in a microwave oven is this. 2.45 gigahertz, or gigahertz. So at this point, they are saying we need to calculate its wavelength. So we note the data so that lambda is what? Okay, they are saying calculate the wavelength. So the wavelength equals a question mark. But the frequency of radiation in the microwave oven is this. What is the frequency? So the frequency is 2,45 gigahertz or gigahertz. So what is the what is the scientific notation for the GHz, Luyanda?
I'm not sure.
Okay, because what is the okay, because the G is a prefix. The G is a prefix. So now because it is a prefix, most definitely it stands for something. So it stands for times 10 to the power 9 in scientific notation. So it is 2,45 times 10 to the 9th power hertz. So that is what you get. Okay, now there's something that that we have next. So you have the C. And C, we said that it is the speed of light in a vacuum, and it is a constant, and therefore it is 3 times 10 to the power 8 meters per second, like so. Right, so we need the wavelength, so we need to remember what we have here. Right, we note that we remember that we have C equals F lambda, like this. And so how are we able to rearrange these and make lambda the subject? What is lambda here? If you want to make lambda the subject, what is it, Luyanda?
C over F equals the lambda.
Well done, well done. So in other words, C over F equals lambda. How did you get that answer, Luyanda?
That triangle method.
Yeah, there's a triangle, so you can use a triangle and you can put this here. So, and also you can do it like this, and you can put here the F and then the lambda, like just to follow the order. So you can put the F here and then the lambda there. So, so you continue. Okay, so now if you're looking at the fact that C equals F lambda, so you can see that from the triangle, lambda equals C over F. So we continue. So lambda equals C over F. Right. So what is C? We said it's 3 times 10 to the 8th power meters per second. What is the wavelength there? No, the frequency.
2,5 times 10 to the power of 9.
Well done. You are a superstar. 2,45 times 10 to the power 9 hertz for the gigahertz. So now you have the division. Okay, if you use a calculator, what do you get here, Leander? Are you able to try with your calculator to see what answer you're getting?
Yes.
Let me know when you're done, please.
0,122.
Well done. It is actually 0,12 meters. You can move the decimal point to 1, 2, 3 places. So if you want to move it 1, 2, 3 places, so it becomes 120 times 10 to the minus 3 meters. Okay, now the 10 to the minus 3 is the milli. So you have this. You have this. So that therefore becomes the answer. That becomes the answer there. Okay, so the next example. The next example. Right. In the next example, we have the following. What is the frequency? What is the frequency of an electromagnetic wave of wavelength 10 to the minus 8 meters. So what is the formula that is going to be used here to solve this one here? Are you able to identify the formula?
Yeah.
Right, so
It's E equals F.
please come
lambda.
again.
E equals F and lambda.
Okay, yes. Is C equals F lambda. That is the formula. And then obviously now we want to find the frequency. And we can remember that if this is the case and you have C equals F lambda, and you remember the triangle we just drew like so, and we realize that you can perform partitions like this, and C equals F lambda. So now we want to get the unknown here, and they are saying what is the frequency. So what will the frequency be here, Leander?
I don't know.
Please come again. What
I'm
is
not
F?
sure.
If you make F the subject of this equation, what is the formula?
F equals C over lambda.
Well done. So F equals C over lambda. F is C over lambda. So in other words, F is C over lambda. So that in the end, C is what? It is 3 times 10 to the 8th power meters per second. And the wavelength. What is the wavelength? We've got here. So obviously, you remember the data that we need. So they're saying what is the frequency. So and obviously the that's what they want. The wavelength. What is the wavelength? Times 10 to the minus 8. So C is 3 times 10 to the 8th power meters per second. So it's times 10 to, like this. So the wavelength, therefore, it's going to be actually times 10 to the minus 8. 10 to the minus 8 meters, that is the wavelength. And therefore, we perform division. If you use your calculator, what we get is the answer here, Luyanda.
Three times 10 to the power 16.
Well done. It is exactly 3 times 10 to the power 16 hertz. Hertz, or just per second. Just per second. Because here, if you look at these here, what we have is the meter is going to cancel the meter, and we have per second, like that. Right. We have little problems here that are very small. There is what we call the particle nature of electromagnetic radiation. But before I discuss that, I want us to look at examples. Let's look at these particular examples. So there are 2 examples. Now, example number 1 is as follows. You need to be able to calculate the frequency. Right, calculate the frequency of visible light. Calculate the frequency of visible light with a wavelength of 6 times 10 6 times 10 to the minus 7. Calculate the wavelength Right, calculate the wavelength of an electromagnetic wave. Right. Electromagnetic wave with a frequency. Right. Frequency of 10 to the power 12 hertz. And we present a solution to this one here. Right, let's look at the solution to this here, step by step. Right, so, but if you look at the first point, calculate the frequency. Okay, because they're saying calculate the frequency, we write down the data. And in writing down our data, the frequency is what they want. So they're saying calculate the frequency of visible light with a wavelength of 6 times 10 to the minus 7. So the wavelength is actually 6 times 10 to the minus 7 meters. And we write down our triangle here, and we know from the triangle that obviously our formula is C is equal to F lambda. So in other words, C is equal to F lambda. Then if this is the case, we want to find the frequency. So what is the formula for the frequency? If you make the frequency the subject of this equation, what do we get, Luyanda? What do we get, Luyanda?
Frequency equals C over lambda.
Yes, so we can see that the frequency here is C over lambda. So you can say the frequency is actually C over lambda. What is C here?
6 times 10 to the power of minus 7.
Yes, that is the wavelength. So so we continue. We continue. Right, so we know C is 3 times 10 to the 8th power. So C is 3 times 10 to the 8th power. Lambda is 6 times 10 to the minus 7 meters. So we continue. Right, so we continue. Right, so what is the answer to this here? Use your calculator, please, Luyanda, to get the answer to this.
5 times 10 to the power of 14.
Right, you're getting 5 times 10 to the 14th power. And now this is going to be in hertz. Right, so we continue. Right, we continue. Right. We continue. Okay, so this is actually what we have, but yeah, I'll have to sort of verify that Luyanda is correct. So I'm gonna use my device also to make sure that the answer you gave is the correct one. Um, right. Right, so because at this point, what we have here is we have exactly the 3 times 10 to the 8th power. I'm just trying to check if you did the correct calculation here, so that we get correct answers here, because that is extremely important. Right, so right, so we check that. Okay. Right, we continue. Right, so obviously this looks very, very correct here. Right, so as this looks very, very correct, as we said, need to always check our answers to make sure that we get correct answers. Otherwise, then we shall be making terrible blunders if we do not have our answers actually verified. So we must always verify our answers to make sure that we get the correct answers. Sorry. Right, so we have then 6 times 10 in the denominator to the power minus 7. Yeah, like that. Okay. Okay. Okay, so we continue. Right, so If you're getting this answer, then, and now this is therefore the frequency, and you're getting this as the frequency. Okay, now that looks so right there. That looks so right there. Okay, we continue to do a couple of these particular calculations, and obviously we get the answer. Now, the couple of ways you can as well use to do this, because you can take your numbers and say, for instance, 3 divided by 6, and 3 divided by 6 is like 1/2, which is 0.5, and this one is 10 to the 15th power, etc. So that actually gives you the 10 to the 14th power. So it's all good and well. It's all good and well. Right. It's all good and well. So we continue.
Yes.
We continue. Okay, this is very easy stuff. Um, okay. Right, let's look at number 2 now. Ruyanda, number 2 says calculate the wavelength of an electromagnetic. Calculate the wavelength of an electromagnetic wave with the frequency of this. So let's look at the second option. Right, in the second option, obviously you deal with the data. So we continue. We continue. Right. Okay, so yeah, we actually get these finished up. So now let's do number 2, but we want to calculate the wavelength. So we're looking for lambda. So lambda equals sort of a question mark. And then now we are looking actually the fact that we want to find the wavelength of an electromagnetic wave with a frequency of this much. So the frequency is 10 to the power 12 hertz. Right. So right. Right. So now we are interested in, but we know the speed of light in vacuum. Right. So right. Which is 3 times 10 to the 8th power meters per second. All right. So now right. So we continue quickly. Right. Do you remember the triangle there, Luyando?
Yes.
Right. So the triangle is like this, and C is F lambda. So you know that C is F lambda. So what is then the wavelength? If we make wavelength the subject, what is the formula?
Lambda equals C over F.
Well done. So lambda equals C over F. Right. So lambda equals C over F. What is C there? Okay. I mean lambda equals C over F. Right. We mean lambda equals C over F. Okay. If you look at this, lambda equals C over F. And C is right. Right, so the C is 3 times 10 to the 8th power meters per second divided by F is 10 to the 12th power hertz. So which means therefore lambda is equal to
3 meters.
what do you think the answer is, Leander?
3 meters.
Okay, yeah, you got it. You got 3. Is it 3?
Yes, I
Well
got 3.
done. Yeah, that looks very correct. 3 meters. So you continue. Right, so that would be the answer over here. And then we proceed to do more calculations. We proceed to do more calculations. Okay, so now let's look at the next question. Let's look at the next question. Right. Let's look at the next one. So, right. Okay, now there are a couple of things that are very important for us to sort of mention here. Right. So let's discuss the particle nature. Right. The particle nature of electromagnetic. Right. The particle nature of electromagnetic radiation. And we discuss the photon. Right, and what the photon is, and in particular, how it fits into everything. So now, um, the certain things I want us to discuss here. Right. So, yeah, okay. Okay, this is sort of a little topic. This is sort of a little topic. So now I want us to look at the fact that light or electromagnetic waves right, electromagnetic waves which we call the EM waves. Could display typical wave nature and particle nature. Okay. Right. Now, I want us to realize that radiation of energy, right? Radiation of energy um right. We continue. Radiation of energy. Okay. Right. Radiation of energy is not a continuous process. Right. It's not a continuous process. Right. So would mention that in 1901, Max Planck um, made the following assumptions. Right, made the following assumptions. What are the assumptions? Okay, assumption number one was that energy is radiated or absorbed in packages or what you call quanta. Right, so in 1901, Max Planck made the following assumptions. The assumption number one was that energy is radiated or absorbed in packages or quanta. Number two, each quantum of energy consists of a fixed amount A fixed amount of energy. E, which is equal to HF, where H is a universal constant. Is a universal constant. Right, and this is called Planck. Planck's constant. Right. And F is the frequency. Of the radiation. So E equals HF. Number 3. He made the assumption that only whole numbers of quanta can be radiated. Radiated. So now, okay, so I want us to say more. Right, there's a certain scientist who was called Albert Einstein. So in 1905, Albert Einstein called these energy packages called them photons. Now, it leads us to define a photon. What is a photon? What do you think a photon is, Luyanda? What is a photon?
A particle.
Please come again.
A particle.
Yes, a photon is a particle, right? A photon is a particle. So a photon is an energy package. It's an energy package associated with electromagnetic radiation. or light. So we have to find now a photon. So a photon is an energy package associated with electromagnetic radiation or light. So obviously, I mean, you can refer to that as a particle, is a particle. Okay, so yeah. Right. So we continue. Right. So a photon is an energy package associated with electromagnetic radiation or light. So obviously you can call that a photon is an energy particle. It's a package, so one can call it a particle, sort of an energy particle. Okay, now next thing that we discuss here. And this means, therefore, that E equals HF is the energy of a photon. E equals HF is the energy of a what? Of a photon. But I want us to discuss photoelectric effect. What is photoelectric effect, Leander?
I'm not sure.
Okay. I want to start as follows and say the particle nature of light was first used as a model to explain why light could eject electrons from the surface from the surface of certain metals, right, of certain metals. Right, so now let's look at this. Right, let's look at this carefully. This effect, right, this effect is called the photoelectric effect. Which is the loss. So this one refers to the loss of electrons, right, of electrons by certain metals. when exposed to light. When exposed to light. When exposed to light. Right. This effect is called photoelectric effect. So obviously, I want us to just have a sense of photoelectric effect. The particle nature of light was first used as a model to explain why light could eject electrons. Right, so we're looking at light that is able to eject electrons from the surface of certain metals. This effect is called the photoelectric effect, which is, okay, photoelectric effect is the loss of electrons by certain metals when exposed to light. Note that one. So it is, what is photoelectric effect? So we note that photoelectric effect simply refers to the loss of electrons by certain metals when exposed to light. So yeah, this effect is called the photoelectric effect, which is photoelectric effect means the loss of electrons by certain metals when exposed to light. So when light is shown on certain metals, those metals lose electrons. And the loss of the electrons is called photoelectric effect because photo means light. Photo means light. So if you are dealing with photoelectric effect, we are really saying when you take light and you shine the light on a metal surface, then electrons pop out of the metal surface. They pop out, they jump out. And because they jump out, the jumping out of the electrons is called photoelectric effect. Okay, I want us to discuss this and look at some examples. So, I mean, we know that E equals HF. This one refers to the energy of a photon. Now, so C equals F lambda. C equals F lambda. So in other words, now, what is the frequency here? What is the formula for the frequency? Luyanda? F is equal to what?
Lambda.
Yes, F equals C over lambda. Because F equals C over lambda, we can take the F and we can put it into the equation. We can put it here. If we take the F, we put it there, we get another equation, H, which is rather E equals H C over lambda. H C over lambda, like this. HC over lambda. Yeah, AHC over lambda. That's what I want to write here. Right, HC over lambda. Like so. Okay, so this one is another equation that we can use to calculate the energy of a photon. So we can use either HF or we can use HC over lambda. But obviously we have the two constants that we know. And we know that at this point, we have that our H is equal to what? 6,63 times 10 to the minus 34 joules second. And then now you also have C. Three times 10 to the power 8 meters per second. So that this is the speed of the waves in vacuum, the speed of light in vacuum. And this is what you call the Planck's constant. Right, the H is called Planck's constant. Right, by Max Planck. Right, Planck's constant. So we continue. We continue. So let's continue right now. Let's look at a couple of examples on this. Like 2 examples. Right. Right, let's look at 2 examples. Calculate the energy of a photon of green light. Right, of green light that has a frequency of 6 times 10 to the 14th power hertz. Number 2, a photon of UV light, okay, something called the ultraviolet light. Violet light carries 4,95 times 10 to the minus 19 joules of energy. Calculate the wavelength. Number 2. Calculate the wavelength of ultraviolet. Right, ultraviolet light. If H is 6,6 times 10 to the minus 34 joules second. Let's look at the solution to this. Let's look at the solution to this. Okay, now, if you need to calculate the energy of a photon of green light, that is a frequency of 6 times 10 to, so we need the energy. So E equals a question mark. So we look at number 1 and we write down the data. and to calculate the energy. So it means that E equals a question mark. That's what we want. Of a photon of green light that has a frequency of this much. Right, what is the frequency? 6 times 10 to the 14th power hertz. 6 times 10 to the 14th power hertz. So the hertz can also be written as per second, which means H equals HF. What is H, the Planck's constant, Luyanda? What is H equal to as a number? 6,6, right?
Yeah.
Good. 6,6 times 10 to minus 34. Can put here joules second. F. Okay, now 14 per second. So if you use a calculator, 6,6 times everything here gives us 3,96 times 10. Right, so times 10 to the power minus 19 joules. You can use your calculator and tell me what you're getting here, Luanda. If you do 6,6 times 10 to the minus 34 times 6 times 10 to the power 14, can you verify that this answer is correct? Tell me what you're getting if you multiply these two things on your calculator, please, Luanda. Okay. Please. Right.
Got the same.
You got the same answer. Right. The next question is obvious, and it says that a photon of ultraviolet light carries 4,95 times 10 to the minus 19 joules of energy. So the energy is 4,95 times 10 to the minus 19 in number 2. Right, so we have that the energy. So write down some data here first and foremost. So which means therefore the energy (4,95 times 10 to the minus 19 joules). Okay, this is the energy. What is Planck's constant H? 6,6 times 10 to the power minus 34 joules. We need to calculate the wavelength of the ultraviolet light if H is this. So we need the wavelength, calculate the wavelength. So we're looking for lambda. Right, so lambda is a question mark, like so. So what formula do we use right now? Because we know that E equals HF. But we said that it is also HC over lambda. Number 2. So if E equals HC over lambda, what is lambda? the same as, Luyanda?
H times C
So
over
lambda, so
over
the lambda
over
goes there and the E goes there. So it becomes HC over E. HC over E. All right. That is what we're getting. So what is H the same as? 6,6 times 10 to minus 34. 3 times 10 to the 8th power. E, the energy is 4,95 times 10 joules. What is the energy here? So if you use a calculator, what do you get here, Luyanda, if you use a calculator? You
I
done,
got
Luyanda?
yes, I got
What?
0,0000004.
Okay, good. So it is approximately 4 times 10 to the minus 7. Right, to the minus 7 meters. But it is exactly also the same as, you can write it as, because it is this, you can put 4 zeros there because this is like 0.0. But if you move the decimal place is 2 times towards the right, so this is going to be minus 9. Okay, 2 times to the right, we have a minus 9. So that lambda is 400 nanometers. 400 nanometers. 400 nanometers. Okay, I want us to have a discussion about a couple of other things. Let us discuss the main types. The main types of radiation. Main types of radiation in the EM spectrum. EM spectrum. And obviously the EM stands for electromagnetic spectrum. Right, electromagnetic spectrum. So let's look at this one. What are the main types of radiation in the EM spectrum? Number one, radio waves. Radio waves. Okay, there are main types. There are several types of radiation in the EM spectrum. Radio waves are among those. But let us first okay. So let us first define this one. I want to first mention something here. I want to first mention something here. The electromagnetic spectrum refers to the range of wavelengths over which electromagnetic waves are spread. Okay. So obviously here we are discussing the electromagnetic spectrum. What is the electromagnetic spectrum? The electromagnetic spectrum is the range of wavelengths over which electromagnetic waves are spread. Right, so now we have the order of colors in the visible spectrum. The order of colors in the visible spectrum. Let us look at the order of the colors here. Right. Continue, please. So here we cut a small slice of the spectrum. Another little slice here. another slice here. But here we're going to put the red. Put outside here. Red. And then the next thing we have orange. After orange is what, Leander? Yellow?
Yellow.
Okay. After yellow is what, Leander?
Violet.
Okay, that's fine.
Green.
Green. After green is what, Leander?
Blue.
Well done. Excellent stuff. Blue. After blue, okay, I'm just still writing blue here. Okay, so this one is blue. After blue is what, Leander?
Violet.
After blue is indigo. That's fine. I know you're still learning these. After blue is indigo. Right, indigo. After indigo is violet. So this here, what they form is the acronym called the ROYGBIV. ROYGBIV. What does ROYGBIV stand for, Rianda?
Red, orange, yellow, green, blue, indigo, violet.
Well done. Excellent stuff. Okay, thank you for that. Now, I want us to mention the fact that here you have the wavelength, for example, at the red part of the spectrum, 8 by 10 to the minus 7 meters. And then you have 4 times, so this one goes with the red part of the spectrum, but you also have the violet part of the spectrum, which is 4 times 10 to the power minus 7. So now, if you look at the fact that now we have wavelength, right? Wavelength. So, okay, you have the wavelength now. So the wavelength sort of ranges like this. So if it ranges that way, you have, for instance, at the violet part of the spectrum, which is about 4 times 10 to the minus 7, but 8 times 10 to the minus 7 on the red part. But this is the order of the colors in what you call the visible spectrum. And most importantly, we make note of the fact that this denotes the wavelength up there in view of the part of the visible spectrum. But let us now just list down all the main types of radiation that you need to learn. The UHF and the VHF and the radio waves and other things. Let's just talk about these a little bit more. Right, we're back to discuss in detail the main types of radiation in the EM spectrum. In the EM spectrum. So We continue. Let's speak about the radio waves. Right, let's speak about the radio waves. Okay, now this one's here. What are they? And we say something about the radio waves. Right. So they are the longest. The longest EM waves and are generated by a radio transmitter. Okay, they are the longest electromagnetic waves, radio waves. They are the longest. Now, the key word here is the word longest. So they are basically the longest electromagnetic waves and are generated by a radio transmitter. Now, the VHF. Right, we speak about the VHF as the very high frequency radio waves. Very high frequency um, radio waves. Right, so I have this one's the VHF. They basically have a wavelength of approximately 3 meters. Right, and used for FM broadcasts. Next, we also have the UHF. What does UHF stand for, Luyando?
I'm not sure.
Please come again.
I'm not sure.
Okay, UHF stands for the ultra high frequency. Ultra high frequency waves have a shorter wavelength. Which is 0.1 meters to 1 meter. And I used for television. For television broadcasting. Used for television what? Broadcasting. Okay, if you cook in the kitchen there, normally you are using the microwaves. Let's speak about the microwaves that are used in the kitchen. You know a microwave oven? Do you know a microwave oven, Luyanda?
Yes.
Okay, right, microwaves. Let's speak about these microwaves. Right, right. So microwaves have the shortest wavelength. Microwaves, they have the shortest wavelength of the radio waves. So these microwaves are under radio waves because now what are we talking about here? We're speaking about what we call the radio waves. We're speaking about the radio waves. So we are effectively then saying the radio waves, the microwaves we're talking about are under radio waves. Okay, let's speak about the microwaves. They have the shortest wavelength of the radio waves and are used. Okay, and are used particularly particularly for communications satellites, right, for communications satellites, right, satellites and telephones. And telephones, as well as in what you call radar systems, radar systems. So the microwaves are used in radar systems. They're used in satellites and telephones that we have access to and that we use daily and so on to communicate. But also, most importantly, the microwaves used in microwave ovens. Let's speak about the microwave ovens. Right, in microwave ovens, what happens in the microwave oven? So the microwaves used in microwave ovens for heating and cooking. Food have a wavelength, have a wavelength of about 120 millimeters. Okay, now we're speaking about the cooking that we do. Okay, so there are certain microwaves that are used in the microwave ovens. So the microwaves are under radio waves. So, but the microwaves that are used in the ovens, in the kitchens for heating and cooking food, so for cooking and heating, have a wavelength of about 120 millimeters. Okay, the next type of these waves is what you call the infrared radiation. Number two, we spoke about radio waves, and under radio waves, we found the microwaves and so on used for cooking, satellites, and telephones. But now we speak about the infrared radiation. Right, what does infrared radiation mean? What kind of radiation is this? So infrared radiation is emitted by all hot objects. By all hot objects, and is called heat rays. They have a considerable heating effect. Heating effect. So we check this one. When absorbed. Okay. And they are invisible. They are invisible. Infrared radiation. Let's speak about infrared radiation. Infrared radiation is emitted by all hot objects and is called heat rays. So the rays from a hot object are called the heat rays. They have a considerable heating effect when absorbed. They are invisible. Those heat rays are invisible, and that is called infrared radiation. Infrared radiation. Right, so let's speak about the UV radiation. What does UV radiation stand for, Luyander?
Ultraviolet.
Ultraviolet, well done. Before that, let's speak about visible light. Visible light. Right, so visible light constitutes 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 about, or rather constitutes a very small part of EM spectrum. It can be observed by the human eye, right, by the human eye. And affects photographic film. Photographic film. It ranges from 4 times 10 to the minus 7 red light to 8 times 10 to the minus 7 meters violet light. Okay, the order of colors. The order of colors in the visible spectrum is shown in the ROYGBIV diagram. Okay. So we have this. Visible light. Okay, visible light constitutes a very small part of the EM spectrum. We note that the visible light is just a small portion of the electromagnetic spectrum. It can be observed by the human eye and affects photographic film. So we are able to see the visible spectrum, or what we call visible light, right? But also it is observed by the human eye and affects photographic film. It ranges from 4 times 10 to the minus 7 meters for the red light to the violet. Obviously, we saw this in the ROYGBIV diagram. The order of the colors, in the visible spectrum is shown in the ROYGBIV diagram above. So we looked at the ROYGBIV diagram and we drew the ROYGBIV diagram, and we agree, therefore, that at this point we're able to see red color, orange, and so on in the ROYGBIV diagram. But we know that red has a wavelength of 4 times 10 to the minus 7, and violet has a wavelength of 8 times 10 to the minus 7. So red is 4 times 10 to the minus 7. Violet is 8 times 10 to the minus 7. So that is what we have, and we saw that in the diagram here, where the violet itself is actually 8 times 10 to the, the red is 4 times 10 to the minus 7, or the other way around. Okay, so look at that very carefully and realize that let's just stick to this, but also realize that you have the frequencies and the wavelengths changing according to the diagram. Okay, we can stick to red is having 8 times 10 to the minus 7, and violet is 4 times 10 to the minus 7. Okay, so you note that diagram and think of it very carefully. Note the diagram and think of it very carefully. Right. Right. So we note that and think of that very carefully. So this is the correct one. So see what was written here. Right. Need to just check. Okay, because now obviously we're looking at the red in the, I want us to just to make mention of the fact that the red is at 8 and the violet is at 4. Is at 4. The red is at 8. Okay, so we saw that in the order of the colors in the visible spectrum. Okay, I want us to speak more about the UV. That is number 4. Ultraviolet. Ultraviolet radiation. UV. Right, so ultraviolet radiation is the invisible. Can cause sunburn, and affects photographic film. Photographic film. Right, and affects photographic film. It causes certain substances to fluoresce. Right, to fluoresce and can ionize in air and can ionize air. Okay, we're speaking about, let's say a little bit more about the UV radiation. What is it? Okay, this ultraviolet radiation, what is it? Is invisible. You can't see it with the naked eye. Can cause sunburn and affects photographic film. It causes certain substances to fluoresce and can ionize air. Okay, so this is UV radiation. And obviously, this form of radiation can cause sunburn because it is mostly from the sun. If you're just in the sun for too long, you are likely to be exposed to UV radiation from the sun, and it can cause sunburn. And now you look at your skin and realize that, my goodness, ooh, you scorched up, you bent, sore. Now, I want us to speak about the next form of the radiation in the EM spectrum. So this was number 4. Number 5, the X-rays. These penetrating rays. These penetrating rays. These penetrating rays. The X-rays are penetrating. So these penetrating rays are released when substances are bombarded. Right, when substances are bombarded with high speed electrons. High speed electrons, they affect photographic films and are used to examine the human body. The human body for broken bones. So let's speak about the X-rays. What are X-rays? What kind of part of the spectrum is this? What kind of the EM spectrum is this? These penetrating rays, they penetrate, they go through the human flesh, these ones. If they are shown on you, these X-rays on your body, on your chest, etc., these penetrating rays are released when substances are bombarded with high-speed electrons. High-speed electrons, they can be bombarded on your leg. If they are bombarded on your leg, then they want to see the bones in your leg. If you fell down and you broke your leg, if you broke your leg, they want to see if the bones are broken, and the X-rays are used to for that. So they affect photographic films and are used to examine the human body for broken bones. Okay, so they're able to help us see the broken bones. Right. So, but now I want to say more about the X-rays here. X-rays have high energy, have high energy, and they can penetrate, can penetrate can penetrate the human body. Right. The human body. X-rays can damage can damage living tissue living tissue and can kill small organisms and certain types. All right. And certain types of cancer cells. All right, cancer cells. Okay, now X-rays have high energy and can penetrate the human body. They're very high energy, but X-rays can damage living tissue and can kill small organisms and certain types of cancer cells. So in other words, they can kill certain types of cancer cells in the human body if somebody has cancer. But now, 6, the gamma rays. The gamma rays. What are gamma rays? Do you know gamma rays? What are gamma rays? Well, gamma rays are part of the electromagnetic radiation. They are electromagnetic radiation. They are in the EM spectrum. But what are they, these gamma rays? Do you know what gamma rays are, Luyanda?
No.
No. Okay. These rays are emitted naturally during they're emitted naturally during transformations. Transformations that occur in the nuclei of atoms of radioactive elements. Radioactive elements. Radioactive elements. Right. Radioactive elements. So these rays are emitted naturally during transformations that occur in the nuclei of atoms of radioactive elements. But here is a comparison that in particular, the gamma rays are even more penetrating than X-rays. Okay, they're able to penetrate Right, able to penetrate several centimeters of lead They have high energy and possess all properties of X-rays. But to a greater degree. Right, but to a greater degree. Gamma rays are used to treat medical conditions conditions like cancer. They're used to treat cancer. Okay. So I want us to look at some problems and at least a question that would sort of assist us here to here is an activity. Okay, right. Our time is up. So I will see you again next time. Okay, so you need to take this discussion, watch the video, and make sure that you take this video, you write down these things in your book, because I will test you on these things. Okay.
Okay.
Yeah, I'll give you some tests on these things. So you need to make sure that you understand these things. But I can see that our time is up. So, but most importantly, I must thank you for joining us, because I don't want to keep you for very long. Right, our time is up. I'll see you again next time. But when I meet you later on today, we shall do mathematics. But thanks a lot for your time, and goodbye to you.
Bye.
Thanks. Goodbye.